Hello, this is David G. Today, we're going to talk about some knowledge on energy storage. Well, it is certainly very critical for the 21st century. And look at our beautiful globe, right? And we only have one right now, right? So we have to take better of this planet. Well, let me get started with a very stunning fact. That is 61% of our total energy harvested right here in the United States is wasted by being released as heat. Okay, so if you're driving a car, the efficiency for just internal combustion engine car, regular one, is only around 18% to maybe 25%. Right, a hybrid one can be better. Certainly, electric vehicles will be very efficient, right? And where the energy goes for the internal combustion engine cars, 80% just went away from the muffler, right? That's it. And so look at how much petroleum we need, and mainly for transportation, right? That's a big problem. And petroleum and coal and natural gas, and particularly petroleum, is is not very domestic so far, and it is fossil fuels. And coal is really dirty. That's a problem, right? It contains substances like mineral, mercury. If you burn a lot of coal, well, it's going to be an issue for the environment. Now, if you look at other sources, right, we use a lot of natural gas and coal and for electricity. And electricity, actually, you need a lot of different sources like solar and nuclear and wind. As of in 2012, the renewable energies like solar and wind, they are not a major source of electricity, right? And in the whole world, it is not so far. And nuclear has been pretty stable source of electricity for the last several decades in the United States, and it hasn't been increased for quite a while. And hydro is geographically limited. Right here in Oregon, we're lucky we have a lot of hydro, so our electricity can be pretty green. So geothermal, that's a minor source. Natural gas in the recent years becoming a major supplement for coal and petroleum, right? And it's cleaner. It's definitely cleaner, and it's quite domestic. Well, if you look at here, we need a lot of energy for transportation, industry, and residential commercial. Okay, and now we have a big problem, which is the efficiency. How to improve the efficiency, right? And how to maintain your house. When it's hot, you maintain it cool. When it is cold outside, you maintain it warm and without using a lot of energy. That's a big challenge right now. And this unit's big, quite, right? It's actually 10 to the 18 joules. Anyway, that's this slide. Let's move on. So many people working on renewable energies, and there are quite a few different sources. For example, solar and wind. Right. This is probably a photo taken along the Columbia River bank, and this is a solar farm in Topaz, California, and just by having 9 million solar panels, right, that covers such a large area. But the good thing is it can power 0.16 million homes. Well, the question is, what about the night, right? You have such a huge, volume of electricity pumped into the grid, but during night there's nothing. There's no supply of solar energy anymore, and we have to be aware that the grid is not somewhere you can store energy. So it's the nature of being intermittent, right? And and that's going to give a lot of pressure for the grid. And grid can only transmit electricity, not for storing, right? If we try to, use the grid, the grid can burn, right? It can burn off, and that could be disaster like this. This is actually in 2003, and the whole New England area is now blacking out because the grid problem, right? So it could be very damaging to a lot of different sectors of the society. So to solve that problem, we need to find ways to store our energy. This has been a issue for centuries, right? For centuries. So nature does this really well, right? Solar energy, that's the source of our energy for many different derivatives, like wind, like biomass, right? It's all from solar. So for example, for just hydro energy, right? And what happens is we have large bodies of water, like oceans, and they're gonna evaporate, and the water vapor just goes up to the sky, and they agglomerates into droplets of water. Eventually, they form clouds, which get really darkened. Eventually, get thick, and then they will be too heavy to be held by the air, and they just precipitate down to the ground, right? And that's how we get the raining. And also, if you have the water precipitating on the hills, and they're gonna flow down, right? When they flow down, they will have a lot of energy that we call potential energy, right? Potential energy. You can build dams along the river. Well, it's going to be a serious problem for salmon to swim up, right? So, but anyway, this is actually the whole logic of having hydro energy. Well, we use this method to store our electricity, right? Actually, as of now, it is most likely that the vast majority of electricity is stored all over the world by this method. It's called pumped hydro. Okay, so most countries, they dig a big hole, and they actually dig a big swimming pool. It's a huge swimming pool, right? And they pump water into this reservoir. Okay, hopefully there's not too much sunshine and it's not evaporating too much, and then you can have the water stored here, right? And it contains a lot of potential energy when you need it. So there's a tunnel right here. The energy, the water can be released into the reservoir, and from the reservoir into the dam. Okay, and that will turn around the turbine, generating electricity. Okay, so this way actually is taking probably over 95% or even more of the total energy storage for electricity around the world. Okay, so that's a major method. The problem of this is it is geographically restricted. Right? In a desert, for example, in a metropolitan areas, we won't have the luxury of building such a massive infrastructure, and it's not very nice to live in a neighborhood around this giant pool as well, right? What if there's a crack? So it is very limited, and it has to be around a river, right? You need the river as the source of water. So it cannot be used for all the countries, for all the states or neighborhoods, right? And so that's its limitation. Now another method is called compressed air energy storage. So basically the concept is to utilize the depleted mines, right? And the plant can pump air into the reservoir, and that will increase the pressure. Of course, the whole system must be sealed, right? Must be sealed. Otherwise, if you have a leaking, then the pressure will not be held at a high pressure, right? And then there are gonna be valves. When you need the energy, you can release the air out of the reservoir, and that will turn around the turbine to generate electricity as well, right? So this is also limited, and you have to happen to have a reservoir around that is a depleted mine, right, for minerals or for coals, right? So, but these two methods, pumped hydro and compressed air, they're the two major energy storage tools, but they are also geographically limited. Well, the compressed air concept has been used to design vehicles. Like this car is pumped by air, compressed air, right? But we have to remember that this is not a brand new concept, right? This was contemplated quite a while ago. Well, if you look at this newspaper, you can see that, well, this is totally against the safety rules. You cannot have the regulators without capping. Well, if this regulator is broken off, the whole vehicle could be just like a horizontal flying missile, right? That could be a disaster, and we don't want that. But with modern technology, with better safety procedure, this may be possible, right? Such a car may be possible. It's completely clean, right? There is no emission at all, right? So that's a possibility. Well, another method is called a flywheel energy storage. So this is using kinetic energy to store electricity. So what happens is when we have surplus of electricity, we'll just spin this moving part into the speed that is really fast. And you can imagine that a trick of maintaining a high efficiency is to make sure the friction is as small as possible, right? Otherwise, you're gonna lose the efficiency. So, but such instrument is not gonna be very cheap, right? Any equipment with moving part can be a little bit expensive, right? You can imagine that. Well, but people have been input effort to really build large facilities like this one, right? And this is quite large, and capacity is 20 megawatts. Okay, wow, it's a blue sky, right? Beautiful place. Now, another method is called, well, I'm gonna let you guess, what is the facility here? Is this actually a solar panel, right? Is it a solar panel or by photovoltaic? Well, I will let you guess just for 5 seconds. Okay, so it is not. It is not by solar panels. All these little squares, they are mirrors. They're literally just mirrors, okay? And they're twisted, they're rotating to reflect sunlight toward this reservoir of salt, okay? So you're gonna have the salt becoming molten in this box, okay, literally by the light reflected by these mirrors to this black box, right? The black color helps absorbing all the visible light. Now, the molten salt will be pumped through a factory, a plant that is gonna heat the water into steam, right? We need steam to power the turbine again to generate electricity. So this is a thermal energy relevant facility. Okay, so that is a huge capacity, 392 megawatts, powering 140,000 homes. Okay, so it's in Ivanpah solar electric generating system. Now, that's the schematic of how this operates, right? And you have the reservoir here is flowing, right? You have the hot salt, right, molten salt as a liquid flowing through this steam generator. Eventually they're going to be cooled down, right? The liquid will be cooled down and they flow back, right? They flow back to the reservoir of or receiver. Okay, so the whole concept of doing energy storage is by load leveling, right? Actually, this plot is actually about energy consumption, right, of a neighborhood, right? This is actually energy consumption. So you can see that around, well, 5 p.m. to 6 p.m., right, most people coming home, they start to turn on their air conditioner or heater, and they're going to start cooking. So we're going to need a lot of electricity. So you're going to have a peak right here. And for most utility company, they have to maintain some kind of facility called a peak factory or peak plant. They're going to supply the electricity just for this. And such plant, for most of the time, will be idle, right? Will be just waiting for the uses of a few hours. Well, that's going to be a cost, right? That's going to be a huge cost to maintain such a facility. And of course, such cost, it will be from our bills. Okay, so what if we can actually store our energy, just supply such the peaking hours by renewable energies, right? And that's actually will be very helpful. Okay, so now let me keep moving to talk about something related to, well, a little bit basics of physics and also chemistry. So there are two major devices. One is called capacitors, and the other one is called batteries. Okay, so about capacitors, the mechanism is very straightforward. Say we have a piece of metal right here, and then we apply a bias, okay, or a voltage on the two sides of the metal. Okay, so by having this voltage applied, we're going to build an electric field. Well, this electric field will actually drive electrons, that is the charge carrier in metals, that are free. They can move around. Under the electric field, electrons will move from one end to the other end. Okay, and now we call such a metal being polarized. One end we have surplus of electrons, the excess of electrons. The other one we call that electron holes. Okay, so now what if I just magically cut off the middle part of the metal? We're gonna have the electrons stranded on one side and the electron holes stranded on the other side. Now, in between, there will be still electric field, right? And literally, this is called a capacitor, right? I can just charge this capacitor by applying a voltage like this. Now, what if I want to use the electricity I just stored here? I'll just release this circuit. I will allow the electrons to move through the circuit to the original spot they were, to combine with the electron holes. Then nothing will be polarized. When I say polarized, I mean it is charged. Like this one, I will call it positively charged. This is negatively charged. Okay, or you call this positive electrode, is negative electrode. Well, what I just did by applying a voltage, I call that charging. And now if I release the electrons through the circuit back to this electrode, I call that discharge. Okay, like such. Well, this is actually spontaneous, right? They're just gonna move back and releasing energy electricity. And capacitors typically can discharge really fast, right? Really fast. And this is pure physics. There's no chemistry in it. Well, a capacitor, well, will look like this. We're going to have one plate was charged on a surface, right? So negative charges will be electrons on the surface. The positive will be on the surface of the metal as well. Okay, so that's a simple schematic of the capacitor. And if you are curious about more knowledge on this, I can probably prepare more videos in the future. It is featured by capacitance. The capacitor is characterized by capacitance. And capacitance means the capability of storing charges of the capacitor over a unit voltage, right? Over unit voltage. And it is proportional to the area, to the surface area of the capacitor. It is inversely proportional to the distance between the two plates or two electrodes. Okay, so, well, first capacitor was invented almost simultaneously by two scientists, right? But eventually this device was named as Leyden jar. Well, you may have heard of something called a supercapacitor. Right? Being super means it's going to be great. Well, it's actually a brand name. Supercapacitor is a brand name, and it's also called ultra capacitor. It's also a brand name, right? It's trademark. There's not too much scientific meaning for super or ultra, and more better technical name is called electrochemical capacitor or electrical double layer capacitor. Okay, so the difference between this capacitor and the last is that this capacitor contains something called electrolyte. And electrolyte is nothing but a solution of salt. It's dissolving some certain salt, right? And when the salt gets dissociated in the electrolyte, you're going to have cations and anions, okay? And now, what if I polarize these two electrodes, right? And I polarize this side to be positively charged on the surface. Now, anions will be electrostatically absorbed onto the surface. And now we have a layer of positive charge, right? And we have a layer, I just call this a layer of negative charge. And I call this ensemble as electrical double layer, right? That's one electrical double layer. And conversely, this side is also an electrical double layer. You have the negative charge on the surface of the electrode, and you have positive charge also near the surface, typically within 10 nanometers to the electrode surface, right? That's positive charge. And that's another reason of electrical double layer. So you have two electrical double layers connected by the electrolyte in series. Okay, so, well, you can imagine that is two of these, okay? But the distance are very close between the two layers, very close. That's why this D value will be very small, and then C will be big for sure. And also, such capacitors, they use something called activated carbon. And activated carbon has a lot of surface area per mass, per unit mass, per gram. Okay, so A will be also big. But anyway, so the energy density of such electrochemical capacitors although it's a lot better than the previous versions, there are a few other versions, including the conventional capacitor and also something called an electrolytic capacitor. You can search on that. And this is called electrochemical capacitor or electrical double layer capacitor. It's a lot better now, but the energy density comparing to the state-of-the-art lithium-ion batteries is still less than 10%. Okay, but they can discharge very fast, so they can provide a huge power that lithium-ion batteries may not be able to provide. Right. So that's the little bit fundamentals of the capacitors, including the most recent electrochemical capacitors or supercapacitors. And by the way, this is not a new invention at all. It was invented in 1960s and commercialized around the end of 1970s, I believe. Now let's move on, right? Let's move on to batteries. It actually started from the experiment with the legs of dead frogs. You can search on that, by Galvani, and that is, and he thought there might be some bioelectricity from the legs of the dead frogs. And well, his colleague Volta didn't think so, and Volta thought, okay, there must be some chemistry force and some distinct difference between the two metals. For example, zinc and silver. And well, the difference between the two metals maybe is the cause of some current going through the legs of the frog, and that causes such like the frog legs to stretch or to move. So, and then he designed this pile. Is a battery, is the first version of batteries, is called a voltaic pile. Okay, so you have electrodes of zinc, and then copper, zinc, and copper in between. You have the newspaper soaked by brine, right? Soaked by some salty water as the electrolyte, and also that blocks the electrons to move from one electrode to the other electrode, so that the short circuits won't happen. Okay, so that is the electrode battery, first version of the batteries. Now you may be curious, well, you are using lithium-ion batteries, probably in your cell phone or cameras or laptops, and now we start to use lithium-ion batteries in electric vehicles. Well, what is the mechanism? What is the operation principle of such batteries? We also call such batteries rocking chair batteries. Okay, so, and again, this was first commercialized in 1991, and has been dominant in the market in the last 27 years, right? And I don't see a sign of fading of this battery, especially in the electric vehicle market. So a little bit introduction of the structure of such batteries. You're going to have something called anode and a cathode. So the conventional lithium-ion battery have two electrodes. The anode side is typically graphite or graphitic carbon, depending on how such carbon is made. And the other side typically is layered metal oxide. And such metal oxide, they are featured by the interstitial empty space between metal oxide layers, and empty space can store lithium ions, right? They can store lithium ions, and lithium ions in such two-dimensional interstitial space, they can move around, and typically is fast, right? It's fast. It's like a two-dimensional highway. But later on, people have been using three-dimensional channel-like structure, so on and so forth. Well, so how the battery works? Let me show you this little cartoon. What if we are charging it? When we charge it, we're going to have electrons moving from cathode to anode And simultaneously, the ions, lithium ions, will move from the cathode to the anode as well, like such. Okay, let's play that again. So during charging, both ions and electrons, I will use this blue sphere to note is electrons. Okay, these gray circles, these are lithium ions. Okay, they just move to the anode. That is charging. Well, when it is discharging, it will be like such. They will move back, and we call this rocking chair. Right? We call this rocking chair. So we have the ions moving back and forth, back and forth, back and forth. And the beauty of such reactions is that the structure of both anode and cathode do not vary much, and they're pretty stable. So the structure do not change much, meaning it is quite reversible. You can do this over and over again. Well, not like your lead acid battery. Lead acid battery, the structures of the electrode are completely changing during charging and discharge. And just for cheap lead acid batteries, probably can only run 300 cycles to 500 cycles. In contrast to lithium ion batteries can run maybe 2,000 cycles to 5,000 cycles. Okay, so what is the fundamental in terms of energy? In terms of energy, for chemistry, we just, when we charge the battery, we raise the electrons to a higher energy. This was me actually when I was quite young. So during, for skiing, you're just, you buy a ticket, right? And the lift will bring you to a higher energy. And when you ski down, you're simply discharged, right? It's the same thing for batteries. Now, if you look at this chart, this is called a vacuum level. Vacuum level is like, electrons are free, they are not bound to any atoms. And then when they are really bound by any atoms, we call that, stabilization of electrons. They will be more stabilized. And typically, by definition, we call that negative. Right, that's actually electron energy goes down. Right, energy goes down. They become more stabilized. The energy will be low. So now, if you compare the energy of negative electrode to the energy of positive electrode, still the energy for the electrons in negative electrode are still high. Okay, they are still high. That's why they are more reactive. Okay, and the electrons in positive electrode are low. So when you do the charging process, so basically you increase the energy of electrons from the low energy positive electrode to the negative electrode. Okay, and during discharge, electron spontaneously flow down from negative electrode to the positive electrode. So it is very similar to potential energy or kinetic energy. Well, during charging, we always bring some particles from a lower energy state to a higher energy state. And during discharge, they spontaneously flow back to their lower energy levels. Okay? So, well, for our community, as battery chemist, we design batteries to do load leveling to store renewable energy sources like solar and wind. We do have to pay attention to the cost, right? And what is determining cost? The sustainability. Well, we don't want to actually run out of the elements we rely on for manufacturing of batteries. For example, well, if we use a lot of lithium for storage batteries, like the batteries to store energy from wind or solar, well, we don't have too much lithium. Right? That's actually, well, we'll probably have enough for electric vehicles in the coming decades. But if we use lithium for everything, that won't be really wise. Okay, so then we start to to look around in the periodic table, and this is a really good periodic table. Firstly, designed by Professor Sheehan, and he's actually using different sizes of the letters and the areas in the box to denote the abundancy of elements. And we can see that if we actually switch from lithium, switch from other cobalt to, for example, iron or calcium or sodium, aluminum, magnesium, silicon, carbon, or oxygen, or even water, hydrogen. The prospect of the future sustainability for batteries can be much better. Right? That's actually the motivation for a lot of research people are doing in national labs or universities. Okay, so that's all. I hope you enjoy this video. I hope you can you have got some new information about energy storage. I hope you can actually pay more attention to this area and to my channel. Okay, with this, I want to thank you for your attention.